And I don't have the view graph, but I've seen one that talks about the percent of power, energy usage in the United States anyway, that goes through electrical form in some way, because it involves solar cells, or it involves some electrical generator, or electric motors, electric lighting. It's all part of the energy economy, and that fraction is going up and up. So there's a whole part of the course where we talk about motors, generators, high voltage transmission, all related to the energy economy. So you have some feel on that. One thing that you don't have a good feel for, which is an even bigger part of the energy economy, is nuclear power. How many people here, for example, know the difference between fission and fusion? Okay, that's about 6. The rest of you don't know the difference between fission and fusion. Okay, so we're going to talk about that because, you know, most of us are worried about carbon emissions and global warming, and nuclear power is a big part of that discussion. And what are, you know, why are people afraid of nuclear power, for example? You know, people hear this thing called radiation. What is radiation? Where does nuclear power come from? Where does the energy come from? What's fission? What's fusion? So I'm going to give at least one day, we'll give a lecture just outlining what the main things are there. So it's some idea of an important part of the energy economy. Not related to anything else we did in the course. But if you want to say you know something about the energy economy, the electrical energy economy, it's good to know about that. The other part that we're going to finish up with, starting today actually, is going back to where we started. We started with optics. And mostly in optics we talked about rays of light. And we did all kinds of lenses and imaging systems based on rays of light. We talked a little bit about waves, we talked about diffraction, and so forth. And we talked about electromagnetic waves the last 2 lectures. But I mentioned what we know already, that light can come in particles called photons. And there's certain parts of optics you need to know photons to understand, but that's called photonics. So the photons are the important part. So we're going to talk starting today about light emitters, things that emit light. And we're going to talk next week about things that detect light. And that's going to wrap up the course. For example, why from a practical point of view, as an engineer, do we care about light emitters? Give me one application. Why do we want to emit light?
Computers. Screens.
Screens. Okay, we want to see screens. We want to have light bulbs, right? So clearly, we're going to talk about what's known as light-emitting diodes. And they emit light. You use those in the lab. That one lab where we had a lot of white light sources. What's another reason? Maybe it's not so obvious. All of us depend on light emitters every day, every time we log on. Let's say every time we go online. And if the internet, how does signals get around the internet? We say they go to the cloud. Well, it's not the cloud. What does it mean? And we'll talk later today about optical fiber and what that's all about. And next week we'll talk about lasers, which are related to light-emitting diodes, but they have some more twists, and we'll explain what they are. So that's going to start today. We'll finish it up next week. Nuclear power will get sandwiched in somewhere. And the last thing I want to cover, of course, is light detectors. Considering what we talked all about in the beginning of the course, why is it important to understand light detectors? First part of the course we had, we drew this diagram about 100 times. I had here an object, right? I had a lens. And what was here? what I put here in all these diagrams.
Camera or image?
Pardon me?
Camera, image?
Well, this whole thing was the camera. The lens was the front of the camera. That's what I'm trying to take the picture of. What's back here?
The film.
Film in the olden days. What's in your cell phone? What do we talk about on the midterm? What do we analyze? We had this so-called imaging array, right? Well, what's an imaging array? What is that imaging array? And what limits how good it is? So, what do we want to know? What's an imaging array? How does it work? We don't need any new physics. We've got all the physics we need, but we will put it together in a practical engineering institute. Okay, another kind of light detector many of you don't use on a daily level, at least directly, but you all would agree it's a good thing. And let's go back to the electrification of the energy economy. What's a good light detector? Why would we be interested in light detectors related to the energy economy?
Solar panels.
Pardon?
Solar panels. Solar panels.
Solar cells. Yeah, solar cells. What's a solar cell? How does it work? What makes a good one, what makes a bad one? And we'll see that we have all the basic knowledge we need already to talk about solar cells, and they're very closely related to the imaging arrays that are in the back of your cell phones or in cameras. Matter of fact, it's almost the same thing, just optimized in different ways. So that's where we're going from here on out. Both light emitters, light detectors depend on this concept of photons, so that's why we call it photonics as opposed to classical optics, which just depends on having rays or maybe light with some wavelength in it. Okay. Questions? So that's going to wrap us up. Well, we will be done by next Friday. We will not have any lectures and reading period, assuming I keep standing, through next week. Okay. Anyway, so we have, if you go back, we're going to talk about more things related to energy, and we're going to talk about more things related to imaging, energy and imaging, basically. No more about computation. Except a little bit today, we'll talk about the internet. All right, I need a volunteer. Let's see, who's, Zach, you been up here yet?
I have not.
Yes?
No.
Good, don't start. They're not here. They're floating around a room somewhere? My polarizer? Remember I had those two sheets and we rotated them, the light went through, it didn't go through? Anybody see them? Max, they're not in that bag, are they? There's a chance.
Nope.
I thought I had them because I had the... Okay, well, we remember two polarizers, right? Do you remember them?
Remember what?
I had these two gray plastic sheets, and if I rotated them, no light at all went through?
Yes.
Okay, good. So, remember that. So suppose I have I have some light sources here. So light rays are coming out. And I put here, here's one of those sheets this way. And it's polarized, that when the electric field is this way, it transmits. So there's an electromagnetic wave going up, and it can have an electric field in any direction perpendicular to the wave. The ray is going this way, that's the way of the light. And there's an electric field going in any direction in this plane, perpendicular to the direction it's going. And this polarizer will transmit any component of electric field in and out of the board. Yeah, so this is a light ray, electromagnetic wave going up. It could have an electric field polarized this way, meaning the electric field goes up and down like this. It could be this way, it could be that way, which would be in and out of the board. That would be halfway in between. It could be coming out of the board, which is the same as in, because it goes positive and negative according to the sine wave. And it could be going this way or any direction in this plane, because the ray is perpendicular to the plane. With me? Okay, and this polarizer here only lets the light, the electric field through that is polarized in and out of the board. I drew it in 3D, but this means the electric field is, the ray's going this way, the electric field's going that way. So that's what comes through. And I stick another polarizer up here. So this is polarizer 1, this is polarizer 2. I stick another polarizer up here, which only transmits the any electric field, instead of this way, only transmits electric field going that way.
Like this and that?
Yeah, the light's going up. It can have electric field polarized in any direction. This one only lets through the component of electric field going in that direction. Right. And this one only lets the component of electric field go through this in that direction. So the question is, how much light comes out the top?
No.
None. Okay. Because whatever comes through here, in here, any light here will have an electric field in that direction, because that's all that gets through that polarizer. And then this one says only light with polarization that way gets through, but the way I set it up is this is 90 degrees to that, so nothing can touch it. So here I have no light. Okay. Questions? So it's nothing exciting here. We demonstrated that you guys did in class when you were playing this. Now suppose I have here some magic stuff. Magic stuff. And this stuff has the magic property, some material, that it can rotate polarization. That it rotates, we're going to say it rotates the polarization by 90 degrees. Let's call this the XY, the XY planes. So this is a Z direction here, light's coming up, that's X, that's Y. And any light in the XY plane has a polarization, the XY plane rotates 90 degrees as it goes from here to here. Okay? So let me just say, with no magic stuff, call this light out. Light out at the top. We said it was 0. And with the magic stuff, what happens?
It's the same as light out with P1.
Pardon?
It's the same as light out with P1.
Right, because whatever we're getting coming out here will rotate 90 degrees and by the magic stuff. And then it goes out the top. And it's lined up with the second polarizer goes out. And furthermore, we could consider this light a superposition of half light this way and half light polarized that way. So P1, let's say P1 that passes or transmits E in the X direction, which is 50% of the light that comes in. And so what's going to come out? So then so we'll say light out. It would be 50% of the light in. parts. That's just based on what we placed. So now is the tricky part. This magic stuff not only rotates the light 90 degrees, it's because of these molecules are oriented. If you design it right, the molecules orient themselves in a certain way, and they absorb in one direction, transmit in another direction, things like that. But they have a second property, these materials. They're not, it's not atoms that are fixed in place. When I show you these pictures, I mean these atoms are nailed down. This thing is sort of like a liquid. It's like a gel. And if I do follow, so here was a polarizer 1, and here's polarizer 2. And here's my light. And what I'm going to do is put here a piece of glass, and I'm going to put a metal on it.